So we're going to start off this video with a series of questions. The first is, with gravitational potential energy, do you think that gravitational potential energy could be negative? Why? Well, the answer is yes. Okay, so something that we want to really pay attention to with gravitational potential energy, we calculate using mgh. But this h is really a relative measurement. Okay, so for example, if I'm measuring potential energy, I could say that the ground is height 0, and so if I raise something above the ground, it has some positive height. But I mean, you can go lower than ground level if someone digs a hole, and then in which case you'd have a negative height. Okay, some negative y position to put in height, which means you'd have negative potential energy. And so when we talk about potential energy, what matters isn't how much there is, but how it changes. Okay, and so it's always a relative measurement from one place to another. And so here, if height is changing 0 to negative or positive to 0 or however positive to negative, however it goes, what matters is how much that change is. Okay, and so yes, you can have negative gravitational potential energy. The next question is, can you have negative kinetic energy? The answer is no. Kinetic energy can only be positive because we calculate it by multiplying 1/2 times the mass times velocity squared. Okay, it would not be possible to have negative mass, and for velocity squared to be negative would mean that the velocity was an imaginary number, which is also not possible. Okay, so this has to be positive, and this has to be positive, which means that kinetic energy is also always positive. Okay, so in this video we're going to dig a little deeper into some of the application of conservation of energy, and we're going to be focusing on closed systems. And so really, for this point, just when we say a closed system, we're just saying that all the energy of the system is conserved. And so we're really just going to be going between like potential energy and kinetic energy. Okay, but we will introduce another kind of potential energy. So just like we can give something energy by lifting it up in the air, you can think of potential energy like something has a very short distance to travel to suddenly release a bunch of energy. So like if you have a ball sitting on a cliff, you give it a little shove, and all of a sudden it's going to get all this energy. Okay, well that also can happen when you have a spring that's compressed. If you have an object that's being held up with a compressed spring, if you just move something out of the way, that's going to quickly turn into kinetic energy. So that's energy waiting to be released. Okay, and so we call that elastic potential energy, and I use sub s for a spring. Okay, and if you remember before that work from a spring was equal to 1/2 times k times x final squared minus x initial squared. Okay, and so we can take this and say that potential energy of a spring is 1/2 times k x squared. Okay, and so when we talk about potential energy of a spring, this is the equation we'll use. So now we have 3 energy equations that we can use, and that's going to be a good start for solving the next set of problems that we work through. Here's a scenario we can look at. We have a block that's compressing a spring, and let's say the spring is, well, we won't worry about the spring quite yet. And then we have the block's on a 15-meter hill, and here goes the hill. Okay, and it's going to kind of go down and up and down, and this is probably kind of the ending point. It's going to keep going, I guess, essentially forever. But so this is like a little scenario where we have transformation of energy going on. And before we even analyze it, what's going to be helpful is to make charts and to write equations. And then once we do all that stuff, then we could think about solving for things. Okay, and so to start, we're going to call this position right here up at the top, that will be our first snapshot. We'll call it snapshot A. Okay, and then snapshot B will represent here when it's all the way down at the bottom. Okay, and so the thing that's really helpful about energy is that we only care about the beginning and the end. We can kind of ignore what's going on in between. So at the beginning here, there's two types of energy present. What are those types? Well, since you have a spring that's compressed, we have elastic potential energy, some amount, I'm not sure how much. And then because we're up on this hill, we can say that we also have gravitational potential energy. Okay. What kind of energy do we have here at point B? Well, at point B, we could say that the gravitational potential energy is gone. The elastic potential energy is gone because the spring is no longer compressed. And now we have kinetic energy. Okay, so we can make a nice big bar here. So we have 1, 2, 3, 4, 5, 6, 7 boxes of kinetic energy here. And now we can use this to write an equation. So go ahead and write out an equation for what would be on the left and the right to represent this scenario. So go ahead and write that equation out. Well, for gravitational potential energy, you have mgh. For elastic potential energy, you have 1/2 kx squared. And then for kinetic energy, on this side, you have 1/2 mv squared. Now these ones will go away because they're all 0. Okay? So now from here, we can use this equation to solve for anything. If we knew the velocity at the bottom and the starting height and this information about the spring, we could solve for the mass of the object. If we knew the velocity and information about the spring and we knew the mass, then we could solve for the starting height. Or we could solve here for velocity, we could solve here for the compression of the spring, we could solve for the k value, you could solve for anything here using this relationship. Okay? And so let's say that if the spring is compressed about 0.5 meters, go ahead and solve for the velocity of the object at the bottom of the hill. So solve for v. Okay? As we solve this, something I noticed is that the spring here contributes very little energy. So that was a pretty weak spring, or wasn't compressed very far, because it didn't do really that much compared to the amount of energy contributed by gravitational potential energy. But you solve it, you get 17.24 meters per second as the speed. If you wanted to, we could say like, oh, this hill is x high, and we can make up a section C and figure out maybe how fast it's going there, or how high the hill is there. There's a lot of stuff we can do with this. Okay? So here's another question. We have an object that's 5 meters above the ground, and there's a problem with this question that we're going to ignore for now, and then we'll come back and focus on that problem. But let's say that it's going to fall and hit this object, and it's going to compress it, or the spring, and it's going to compress it 0.8 meters. Now we don't know at what height this spring is, but we're going to say that it's going to compress it to the point that it's at kind of ground level. Okay? And so the question is, given this information, what is the K value or strength of the spring? So I want you to solve for K. Okay, so the stiffness of the spring. And I'm not going to help you at all. I want you to do it from here. So if you want to make a chart in your notes, you can. But go ahead and find out what K is. Alright, so the first step is going to be, I'm going to draw a diagram. And I'm going to show that we start with gravitational potential energy, but no elastic potential energy because the spring is not compressed yet. And then from here, it's going to fall. Now if I graph energy over time, what I can see is that as it falls, the gravitational potential energy is going to decrease until it gets to 0. Okay? And maybe this is by position, we'll say. Okay? And then at some point, it's going to hit the spring, and it's going to increase the energy of the spring. Okay? So in between those points, as it's falling, its velocity is increasing, giving me kinetic energy. Okay? And then that kinetic energy is then going to cause that spring to compress until all the kinetic energy is gone. Okay, so at the beginning we started with gravitational potential energy. At the end we end with elastic potential energy. Now it's true that the velocity was changing as it was falling and we had kinetic energy, but really for energy we just care about the two snapshots we're looking at. So if we want to find K, we want to know when the spring was fully compressed. And so at that point, so we start without kinetic energy, and at that point kinetic energy is all gone again, as is the gravitational potential energy. So we're left with elastic potential energy. So I can write an equation. I can say mgh equals 1/2 kx squared. Okay, and I can solve this. I can say that x is equal to 2 mgh, or k is equal to 2 mgh over x squared, which is equal to, so we get that the K value for the spring is 766 newtons per meter. Okay, that would be the strength of the spring. Okay, so we'll do one more example right now, and for this one, we're going to do a similar thing with the spring, okay, but the change will be that it's going to be a little bit trickier when we talk about energy, because when you compress a spring vertically, the height of the spring changes. Okay, so let's say that we have a scenario here. We have a spring, we'll say K value is, we're going to say 1,000 newtons per meter. And then we have, sorry about that, and then we have an object with, say, a mass of 6 kilograms. And we're going to say that it's about 4 meters above kind of this equilibrium position of the spring. And the question is, well, how far does the spring get compressed? And so here's the problem. So it's going to fall 4 meters before it hits the spring, but if you think about it, the height's going to continue changing as it compresses the spring. So whatever this distance x is going to be part of the height of this. And so when I set up this equation, I say, just like before, I start with gravitational potential energy, and I'm going to end with elastic potential energy, but I have to account for the fact that this is more than 4 meters. Okay, so when I write my equation to solve for this, what should I say that my height is? Well, we're going to say that m is 6, g is 9.8, and height will be 4 plus x. And then on the other side, it's 1/2. The k was 1,000, so 1 times 1,000 times our x squared. And then solving this will get a little bit tricky now, so we'll have to do some simplifying. And then it looks like it's going to be a quadratic. Okay? So I simplify all this, and I end up getting this quadratic, and I'll bring this over to the other side, and when I do the quadratic formula to solve it, or I could graph it, or I could plug it into a quadratic solver, I get that x is about 0.74 or 0.75 meters. I can't quite remember what it was. Okay? And so what happens is, so that means that instead of just falling 4 meters, it's going to fall to 4.74 meters and compress this 0.74 meters. Okay? And if we wanted to plug those numbers in, it should come out to be equal on both sides. But so these are really some examples of how we can use conservation of energy to solve problems. And we can really do some really pretty complex things here. Okay?